Hi everyone and welcome back to my channel. So today we will start with the lecture 4 of cache memory chapter. So today we will discuss the hardware implementation of different cache mapping techniques. So already we know what are the different types of cache mapping, like direct cache mapping and set associative cache mapping. So how actually will I implement those kind of mappings in the hardware? That is what we will understand. So checking first, we will discuss how do I check hit and miss in direct mapping. Okay, how do I check hit and miss? So depending on the procedure, how do I check hit and miss? With the help of that procedure, we will design our whole mux. Okay, it's not mux, sorry, we will design our hardware. So how do I check? First, the address is broken down into three parts in direct mapping. It is broken down into tag, block, and cache block number and the byte offset. Okay, there are three parts of a main memory address, and I compare, like the tag is compared, identifies which memory block is present in the cache. That is where the tag gets compared. Block is the points to the specific block number in the cache. Byte is the exact location within that block. Okay, tag is just the tag of that particular uh, data that is present in the main memory. So what is the process? Process is CPU requests data by providing the memory address. The block number is used to locate the cache block. So first I see the block number and I go to that block of the cache, that block number. Then the tag from the memory address is compared with the tag stored in the cache block. The tag from the memory address is compared with the tag stored in the cache block. Okay, so I compare the tag, whatever tag was given to me through the address and whatever tag is currently present in the cache memory in that particular block. Those two I will compare. If it matches, it's a cache hit, otherwise it's a cache miss. This we have already discussed previously as well, right? So exactly that is what we will implement. So here I have three elements. One is the block offset, that is the byte offset. This one is the my block number, cache block number. This one is the tag. Okay, this one is the block number, this one is the tag. So let's assume, let's take a very basic example, that number of cache blocks is 4. So I have 4 cache blocks. So how many bits I will require? I will require 2 bits. So my cache block number will have length of 2 bits. Okay, cache block number will have length of 2 bits. Okay, now what about the byte offset? So they have told me block size is 16 bytes. So what will be the byte offset? Byte offset will be 4 bits byte. Byte offset will be 4 bits byte. Now main memory address equals to 8 bits. Main memory address is equals to 8 bits. So my whole main memory address is 8 bits. Hence the tag size will be what? Tag size will be 2 bits. So tag size will be 2 bits. Main whole memory size is 8 bits. Okay. So tag is 2 bits. Block this block or the block number is 2 bits. Byte offset is 4 bits. Total it is 8 bits. Now I will have a mux. This mux will have actually 2 select lines to select the cache block number, right? So actually, although it is here showing only one line, actually it has 2 select lines. So this is 2 bits wide, 2 bits. Okay, it is S0 S1. So S1 S0. So basically select lines are something like this. If let's say my cache block number is 00, then I will select the first one. If my cache block number is 01, then I will select the if it was 00, I will select the 0th one. If it is 01, I will select the 1. If it is 10, I will select the second. If it is 11, I will select the third. Okay, like this I will select. Okay, so I have the multiplexers here. So this is a two input select multiplexer, right? So I have 2 select lines here. So that is how I select the block in the cache memory. After selecting the block, what will I do? There will be a comparator. Okay, so this tag will go to a comparator. Okay, and this, right, after selecting whatever tag I have selected, the output will be sent to the multiplier. So there will be a comparator which will compare the main memory address tag which the CPU request for and the tag that I have selected. So that then the comparator will compare this tag and send the result. Now remember again, like this is 0 0, this 0 1, 1 0 and 1 1. Remember this is a 4-bit field because my tag is a, so not 4-bit, tag is 2-bit field. So remember this is a 2-bit field, although only single line is drawn, but it is a 2-bit field. Okay, it is just a 2-bit field, just a 2-bit field. Okay, so remember this thing and that's it, you're sorted, right? So basically what we do, first I select the cache block number, then after selecting the cache block number I pass the tag number, whichever cache block number I have selected, to the comparator. And obviously initially this tag already has been passed to the comparator, so comparator has got 2 inputs, so ultimately output result will be the comparison of these two. If it is equal, then it will be cache hit. If it is not equal, it will be cache miss. So depending on the hit or miss, I will either take this value whatever I have selected, or I have to go to the main memory and select the value. Okay, so that is the very basic working. Now can you tell me what kind of mux I will require, what will be the size of the mux? So it is a what, 4:1 mux, right? It is a 4:1 mux because my select lines are 2. So if I have 2 select lines, that means the mux size will be 4:1. How do I calculate? It is simply 2 raised to power number of bits in cache block number. Okay, is to 1. Number of bits in cache block number is to 1. So how many mux actually I will require? So this will be the size of the mux. So size of the mux will be this, size of mux. That is 2 into number of bits in cache memory block number is to 1. This will be the size of the mux. Actually how many mux will require? Actually we will require not only a single mux, right? Here each mux will give one of the bits of the tag. So if tag is a multi-bit field, so each of them will give the output, right? Its mux can only give 1 bit output, correct? So as I have 2 bits for the tag field, I will need 2 of this mux. So here number of mux required will be equals to number of bits in tag field. Okay, so it is basically, in this case, in this example, we will require how many cache memory bits I have? 2. And how many, so it will be 2 raised to power 2:1 mux, how many? 2. 2 numbers of 2 raised to power 2:1, that is 4:1 mux I will require. So that will be the total number of mux that I will require. So this is the mux. And what is the size of the comparator? What will be the size of the comparator? Size of the comparator, as I am comparing the tag bits, will be equals to the number of tag bits. Size of the comparator will be same as the number of tag bits. That's it. So same size of comparator will be same as the number of bits in the tag field. Okay, so that will be the size of the comparator. So I hope you have understood this basic point. Now yeah, now let's like understand another concept about delays, because whenever like there is a digital block, of course it will have some delay, right? It will have some delay. So this line is propagating here, this mux will have its own delay, and of course there is a comparator will have its own delay. So what is the maximum delay that I can have? So if it is a hit, that I have to go through this mux, so this mux will be the delay for tag selection. Then again I have to compare with the comparator, so I have to wait for the comparator as well. Then only ultimately I will get the result. So total delay will be mux delay plus the comparator delay. This will be the hit latency. This is hit latency because of course the result will not come instantly. I will have some delay to get the result. So that's why it is called latency, hit latency. Okay. Now address breakdown, of course, in now let's check for hit and miss in set associative mapping. What happens in set associative mapping? In set associative mapping, what do we do actually? We first check the set, which set am I lying. So although visually I have told you that visually, right, what happens is I have two sets here. Visually I have told you that this is my 0 1 2 3, okay, and here I have two blocks in the set, but actually what happens is, actually it is not so stored like this. Visually it is like this, but actually how it is stored is, I will explain. It will be somewhat like this. Four, 5, then it is 6, 7. Zero, 1 2 3 4 5 6 7. Okay, so actually, right, actually I will have to delete it again. Basically this whole 0 set is covered for the two cache blocks. So this is set 0, and then this is set 1, and this is set 2, and this is my set 3. Okay, so that's how it is basically covered. That's how it is basically covered. Okay, so how do I select? So now actually I will require like two multiplexers. Because I have to compare two tags. Now how many tags I have to compare? Two tags, right? Because previously, if you remember, I had only a single tag, but here I have two tags. So for this block, let's say this is the tag, and for this block this is the tag. So I have to compare two tags. So I will need double the comparator. Like whatever comparator I required previously, I will need double the comparator. Also I will need two muxes. Why will I need two muxes? So here if you see that, like this is the whole diagram. Okay, let's read this a bit. So set number, I hope you remember how do you calculate the set number. So basically it is equals to main memory block number mod of number of sets in the cache. So in this example, total number of blocks in the cache is 8, but I have only 0 1 2. Okay, 3 sets, not 8, sorry, this is 1 2 3 4 5 6. So I have 6 blocks in the cache memory. Okay, so this set number goes to this one and to this one as well, this multiplexer and this multiplexer as well. Now this multiplexer is used for select of this, like basically we select in a set, we have to select both the tags, right? So the input line here in this case is whatever the input line is, like it is the set number. So this will be the set number, that will be the select line, set number. This will be the input of the mux. This will, let's say this will select the tag number 1 of that particular set, and this mux will select the tag number 2 of that particular set, because each set has two blocks. So I have to select both the tags, and ultimately the output of the mux will come here, right, in two different comparators. Because remember, right, I had to compare both the tags. Whenever one of the comparator is true, then only it will be cache hit. This we have learned. If you are forgetting this, please go into the previous portions. This I have taught there. I have written a key point as well. So whenever there is a true, that is whenever a comparison has become true, that means cache hit has occurred. So I just need one single true. So that's why there is a OR gate. So even if one of the outputs of the comparator is high, that means one of them is true, that means one of them has matched. If they have matched, then the OR gate will be just high. Okay, if they have not matched, then both the comparators will be 0, then the result of the OR gate will be 0 only. Okay, so that's how you will match basically. That's how you will match this. That's how the comparators will work. Okay, so yeah, I hope you have understood. Like here, how many numbers we will require? How many numbers we will require? Everything will doubled. Everything will be doubled. So muxes, previously I only required single, but as it's a two-way set associativity, I will need two mux. Two mux, each of what bits? Each will give me a single bit output, right? So what is the size of my tags? So multiplied by that. Okay, that many number of mux I will require. So let's say if your tag bit is 2 bits, so you will require 2 into how many set numbers you have? You have 0, 1, 2, right? So how many bits can you represent? 2 in 2 bits. In 2 bits you can represent 0, 1, 2. So in this example, what will be the number of mux? So in this example, if I show you in this example, so number of tag bits is how much? Number of tag bits in this case, I don't know. Let's assume it x, because here they have not mentioned what is the number of tag bits. So I don't know. But here I see the set number can be 0, 1, 2. So number of set bits, number of set bits, number of set bits will be equals to what? Number of set bits will be equals to 0, 1, 2. Okay, so I need two set bits to define 0, 1, 2, all these numbers, right? So previously, what was my total number of muxes? So previously, if you see that my total number of muxes was number of bits in the tag field. Now as I have more sets, right? So sets have increased, so muxes will also be increased, right? So the total number of muxes will be number of bits of the set field into the number of bits of the so this is the no in each, sorry, into the number of sets, into the number of sets. So this is a two-way set, because in each set there are two blocks. So into the number of sets into the number of tags. Okay, number of tags in a set. So total number of mux will be equals to, in this case, the total number of mux here will be total number of mux will be equals to what? The whatever was the previous, that will be same, right? Basically the number of tags. Previously I had only a single mux. Of course, depending on the size of the tag, it will be 4, because here I had 4 tags. Here I had 4 tags. So what was the size of the tag here? So size of the tag here, right? Number of bits in the tag field. So what were the number of bits in the tag field? Number of bits in the tag field were, if you remember what we calculated, 2. So I will require 2 field. Sorry, I will require 2 muxes. And here, as the number of here, whatever is the number of tag, like number of bits of the tag, that will be there. Okay, that will be automatically there. So number of bits of tag field, this will be already there, right? Into the number of tags in each set. In a set, how many tags I have? So currently in each set I have 2 tags. So I will need 2 muxes. Why I will need 2 muxes for each set? Because I have to compare all of the tags, right? I have to propagate all of the tags. So that's why into the number of tags, number of tags in each set. This will be the total number of muxes that I require, right? What will be the number of comparators? Number of comparators, again, in each set I have two tags, so I will need two comparators. So both comparator, one of the input will be the actual tag and the other input will be one of the tags of the set and the other tag of the set. So here number of comparators will be equals to number of comparators will be equals to number of tags in each set. Number of tags in each set. Okay, now what are the size of mux and size of the comparator? Size of mux, size of mux, size of mux will be the 2 raised to power number of bits in the cache field. Okay, or yes, number of, because each mux will have, like, it will propagate all the tags, right? So it will be the number of bits in the tag field, 2 raised to power number of bits in the tag field. Oh no, not this, 2 raised to power the set numbers. So how many sets I have, that will be the size of the mux, depending on which set I have to select, right? Either I have to select set 0, set 1 or set 3. So it will be a 3:1 mux, but actually 3:1 mux does not exist. Either 4:1 mux exists or 2:1 mux exists, right? But like generally, if generally these kind of sets are not there, either it is a power of 2. So size of mux will be actually the total number of sets. Okay, total number of sets is to 1. Basically I have to just propagate one of the set, and this propagates only one bit of the tag field. I will need whatever the number of bits I have in the tag field, those many muxes I will require. What is the size of the comparator? Again, size of the comparator will be again same, because we are comparing the tag field. So whatever is the size of the tag field, that is number of bits of the tag field, that will be the size of the comparator. So size of comparator will be number of bits in tag field. Okay, whatever the number of bits in the tag field, that will be the size of the comparator. Now how many OR gates I will require? How many OR gates? I will require only one OR gate. I will require only one OR gate, and of course the comparator output will be either 0 or 1, right? Either it is equals to 0 or 1. So what will be the size of the OR gate? Size of the OR gate will be actually how many number of comparators I have. So in a particular set I have two tags, so size of the OR gate will be 2:1, something like that, right? Because it needs to have two inputs, because I have two tags in a particular set. So this one I will delete actually. This one we don't record. So basically here, if you see OR gate, how many tags are there in each set, that will be the size of the OR gate. So size of OR gate, like number of OR gates is on 1 only, size of OR gate will be the number of tags in each set. This many inputs is what the OR gate will have. Okay, so this will be the size basically of hardware implementation of a set associative mapping. So let's take an example. Let's take a ky set associative where I have k equals to 4. So each set contains k blocks, requires k comparators, one per block in the set. Okay, so if it is four-way set, then that means in each set I have four tags, correct? Each set contains k blocks. Yeah, each set contains k blocks. That is four tags I will have, four blocks. Each set will contain four blocks. That is four tags I will have. Requires k comparator. Why k comparator? Because I will need four comparators, because I have to compare all the four tags with respect to the reference address given by the CPU. So compare all the four tags. Hardware components. So hardware components, how many hardware components will require? Number of mux will be k, that is the number of tags in a set into the tag bits. So exactly whatever I have written here, the same thing, right? Then the size of the mux will be number of sets in the cache memory is to 1. Number of sets in the cache memory, that is total number of sets in the cache memory is to 1. The comparators will be, number will be k, size will be tag bits, because whatever the number of bits I have in the tag, those bits individually I will compare in the comparator, right? That's why I will need k comparators, because I have k tag bits. Or get compiles all the comparators. So size will be equals to it will not be actually equals to tag bits. Size will not be here. Yeah, okay, no, size will not be equals to exactly tag bits. It will be equals to the number of tags present in a section. So it will be k. Okay, it will be k, the number of tags present in a section. So overall, now what will be the delay? Now previously the delay was only mux and comparator. Now I have an extra OR gate, so the hit latency will be mux delay, comparator delay plus OR delay. Now remember, if no delay is mentioned, no delay is mentioned, assume 0. Assume 0. Okay, if no delay is mentioned, assume 0. So now let's understand a fully associative case. So if it's a fully associative case, there is no tag selection. I don't need to select the section, right? I don't need to select the section. So there is no need of a mux. I directly need comparators. So as there is no selection, so there is no need to select a section. That means there is no no that means there is no comparator required, right? There is no comparator required. Okay, no comparator required. So no comparator is required, no mux is required. No mux is required. Okay, only comparator and OR gate. So how many comparator will be required? How many comparator will be required? Number of cache blocks, whatever the number of cache blocks present in the cache memory will be the number of comparators. So number of comparators will be number of cache blocks. Okay, so yeah, and size of the OR gate will be again number of cache blocks. Very simple. Sorry, size of the comparator will be tag bits, because number of tag bits will be the inputs to the comparator, right? And it will compare with the reference tag. It will compare with the reference tag and the tag of the cache memory. Okay, size of the comparator will be number of tag bits. The number of comparators required will be the number of cache blocks. Whatever the number of cache blocks I have, those many comparators are required, because I have to individually compare all the tags. Now what will be the size of the OR gate? number of comparators. The number of comparators is number of cache blocks. So size of the OR gate will be number of cache blocks. That's it. So that is the main crux of this particular fully associative mapping. Now what is the head latency here? As I don't have any mux, so the delay will be caused due to the OR gate, comparator delay, and the OR gate. So delay will be due to the comparator and the OR gate. These are the two causes of delay. Okay, I hope you have understood. Now like the comparison table is given. This is a summary table. You can make a short note about this. So yeah, that was the hardware implementation. Now we will solve few questions. Okay, few questions on this. So let's solve few questions. So in this question we have to consider a 34-bit memory. So I have a 34-bit memory address, okay, which has 512 kilobytes of cache memory. So I have 512 kilobytes of cache memory. The cache is organized as an 8-way set. So it is an 8-way set. That means in each section I will have 8 blocks. So what are the total number of blocks? So because they have given me the block size. Block size is 64 bits. So byte offset will be 6 bits. So the byte offset will be 6 bits. Okay, byte offset will be 6 bits. And then my, like, what are the total number of blocks? Total number of blocks. That is equals to the cache memory size, cache memory size divided by the block size. This will be cache memory. Cache memory size is 512 kilobytes divided by the block size. So block size is uh, 64 bytes, correct? So 64 2 raised to power 8. This is 2 raised to power 8, not 8, sorry, 2 raised to power 9 into 2 raised to power 10 divided by 2 raised to power 6. So this will be overall 2 raised to power 13. This will be my total number of blocks. Now number of sets will be what? Number of sets will be equals to the 2 raised to power 13 divided by the total number of whatever the associativity is. It is 8 associative, so it is 2 cube, so this will be 2 raised to power 10. So number of sets is 2 raised to power 10. What are they asking? What is the number of sets in cache? So this will be the first answer, the number of sets in the cache. Second, what is the answer? Second answer is, what is the size in bits of the tag field per cache block? So size of tag field. So number of sets is this. So number of bits, number of bits, number of bits in set, number of bits of set block will be equals to 10, right? Log of this, that will be equals to 10. That will be equals to 10. Now what are they asking? They are asking me the size of the tag field. So this is 10, so this will be 10, right? Set number. So obviously tag size will be what? This overall is how much? 34 bits. So 34 minus 16 is 18. So 18 bits will be the tag size. So number of bits in tag field will be equals to 34 minus 1 6, sorry, yeah, 1 6, this is equals to 18. So 18 bits will be the answer for the tag field. What about the other one? 3 is the number. What is the number and size of the comparators required for tag matching? So they are asking the number and size of the comparators. So how many comparators will I be requiring? Depending on how many tags I have. So I have 8 tags. So I will be requiring 8 comparators. 8 comparators. And what is the size of each comparator? Each of the size of the tag bits. How many tag bits I have? 18 tag bits. Each of size 18 bits. Okay. So this is the size of the comparator. Now let's do the uh, how many addresses are required to find the byte offset within a cache block. So how many address bits? How many address? Okay, how many? It is 6 bits only, right? Byte offset with 6 bits only. So this we have already calculated. So I don't think this is much required. This is 6 bits only. What is the total amount of extra memory in bytes required for tag bits? So basically they are asking the size of the tag directory. So size. So the fifth one is size of directory. Okay. So the size of tag directory is what? Size of tag directory is equals to, of course, the number of cache blocks. If you remember, for each cache block I have to store the tag, right, into the tag bits. So the number of cache block, what is the number of cache block? Number of cache block is present where here 2 raised to power 13. So it is 2 raised to power 13 into the tag bits. Tag bits is 18. So it will be 2 raised to power 13 into 18 bits. So it will be 2 cube. That is like, if I want, this is bits in bits. In bytes, if I want to write, in bytes, if I want to write, this will be 2 raised to power 10 into 18 bytes, and 2 raised to power 10 is kilo, so it will be 18 kilobytes. So this much amount of extra storage I will require to store all the data. So that's how simple questions come. So that's it basically for this lecture, and we have finished this lecture and all the questions. So everything has been covered in this lecture, and in the next lecture we will discuss about block replacement policy. So we know obviously we have to, whenever there is a cache miss, I have to replace the blocks. So how will I replace the blocks? All those things we will discuss in the next lecture. This lecture was mainly about the hardware implementation of cache memory. So I hope you have enjoyed this lecture. If you did, make sure to hit the like button and comment down below whatever you felt about the lecture, and make sure to comment in the first video so that other people can also learn from these lectures. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.